All right, so first off, I'd like to thank everyone for coming out today. We are the Advanced Combustion Technology Group. My name is Laszlo Kurda, I'm project lead.
My name is Chris Chambers, I'm one of the project engineers.
I'm Leadville Nelson.
And we use tie downs to prevent horizontal motion. Tie downs are the most practical design, so if time permits, we are considering going back and adding, designing stabilizers and adding them to the bottom of the stand that would hook up to the bottom of the scooter to prevent that horizontal motion.
A lot of what we did this quarter was throttle control. Basically what happens with throttle control is there's a speed reading from the dyno and it's fed into the Arduino. The Arduino reads it, processes the information, and then sends a voltage to the servo to adjust using the feedback.
So as Lam said, our main goal this quarter is to figure out the automatic throttle control. So this is a diagram of what we want to do. So the right is a CAD rendering. Down here's the servo. Here's an adapter we machined and a bracket we have mounted. So if you notice, there's two mounting holes here that match up with these two. That's to hold the throttle cables, and then this hole right here indexes with this shaft here, and is held in place with a set screw. And then here's a picture of it mounted. So you can see there's that bracket we were talking about. There's the adapter. Here's the servo mounted with the two throttle, the throttle cable mounting screws, and then indexed with the throttle body here, and here's the throttle.
In order to achieve HCCI conditions within the cylinder, certain parameters must be known. Some of these are intake temperature, coolant temperature, crank arm position, intake pressure, in-cylinder pressure, air-fuel ratio, and exhaust temperature. Fortunately, the majority of these variables we're able to obtain from the scooter's onboard engine control unit. We just tapped into those and we fed that into LabVIEW. Essentially, the LabVIEW code for that is complete. We did need to get two external sensors, and that's the pressure transducer for in-cylinder pressure and the O2 sensor for AFR. But once again, those will all be nicely encompassed within the LabVIEW code that we are working on.
Okay, so next, these are the two sensors that Laszlo just talked about we need to implement. So the first one is the in-cylinder pressure transducer. So it's important for us to be able to figure out how the pressure relates inside the cylinder. So as the piston's moving up and down, we want to get accurate pressure traces as a function of time and crank position. So to do that, we need to tap into that cylinder head. So what we decided to do, what we found a manufacturer that makes spark plugs and will modify them. So the flick line up here, that's the pressure transducer. There's a connector hose, and then if you follow this light blue trace, it goes all the way in the cylinder, and on the right is a picture of the actual spark plug. There's the pressure transducer, there's the cylinder, and then there's the port, the tap for the in-cylinder pressure. Okay, then the second one, we have an O2 sensor, which is used to measure our AFR. The current O2 sensor doesn't fit, so we have to modify the exhaust to mount that. And also one note back on the in-cylinder pressure, the spark plug. As of right now, we don't have a working spark plug. We do have one, but the project was handed to us. They actually ordered the wrong part, and now the manufacturer doesn't make the one that we need. So as of right now, the in-cylinder pressure transducer is kind of up in the air, but we're working to see if we can find a solution.
So we have the throttle control mostly set up, and now we're almost ready to do tests with the dyno in the scooter. Like Chris said before, the pressure transducer is in the air. We're not sure what we do, where we're going to go with it, and we're going to later mount the O2 sensor.
And then again, the goal by the end of spring quarter is to have a baseline emissions analysis, so we're going to be able to take that scooter and run at different RPMs and run that data through our emissions analyzer and be able to find out a baseline emissions analysis. We also want to be able to run autonomous EPA cycle testing, so that requires us to have our throttle control set up as well as our dyno mounted and set up, be able to run EPA emission cycle testing with that. And then we're continually researching viable and cost-effective methods for initiating HCCI. We run into a lot of problems because we can't find equipment small enough to work with our scooter 50cc engine. The few ways that we've thought about doing it is either turbocharging or supercharging. But the problems we're running into, again, is that nobody makes a turbo or supercharger small enough that will handle a 50cc engine. Another way we've discussed doing it is with a system of valves, either increasing the compression ratio in the cylinder, using a system of valves to blow off and shut. And then also, if we can't find a way to make this unit self-contained, what we'll end up having to do is have an auxiliary electric blower to compress that incoming charge. So with that, that's our presentation. We'll open up for questions.